Welcome back to the AI Research Roundup. I am your host, Alex. Today we're diving into a paper from Meta called Photoreal Scene Reconstruction from an Egocentric device. It tackles the challenge of creating highly realistic 3D scenes from wearable cameras. The authors make two key points. First, they use a technique called Visual-Inertial Bundle Adjustment, or VIBA, to precisely track the camera's high-frequency motion. This is crucial for correcting distortions from rolling shutter cameras, which scan an image line by line. Second, they built a new image formation model for Gaussian Splatting that handles these distortions and the camera's high dynamic range. And just to clarify, Gaussian Splatting is a rendering technique that creates 3D scenes by projecting millions of tiny, colorful, semi-transparent shapes called Gaussians. It's really powerful. The best part is, the authors have made the code for this work public. Their GitHub repository has everything you need, including scripts to download sample data, pre-process it, and train your own models to see the results yourself. Alright, so this first figure really puts their method to the test. It shows a side-by-side comparison of an indoor scene with a bookshelf and a TV. The first image is a raw, noisy frame from the camera. The second is a reconstruction using a standard Gaussian splatting method, and you can see it's pretty blurry, especially on the book spines, but then we see their result. The improvement in clarity is incredible. The text is sharp and readable, which they credit to their system correctly handling that rolling shutter distortion. The final image shows the same reconstruction with lifted dynamic range, making the details pop even more. So, to get that incredibly sharp result, the system needs to know exactly how the camera is moving at every single moment. And this next figure shows the hardware that makes it possible. A pair of Project Aria glasses. You can see they're packed with sensors. There's the main RGB camera, but also two specialized SLAM cameras and two inertial measurement units. A SLAM camera, for simultaneous localization and mapping, helps build a map while tracking the glass's position. The inertial measurement units track orientation and rotation at a very high frequency. Together, these sensors provide the super precise trajectory data that's foundational to their whole method. So using the data from those sensors, this next figure really breaks down how the system creates that super precise camera path. Part A shows the full pipeline. It starts with raw measurements and uses a process called visual-inertial odometry, which is essentially using both camera and motion data to make an initial guess of the path. Then, the SLAM system recognizes previously seen locations to refine this path into a closed-loop trajectory, basically correcting for drift. Finally, the Visual-Inertial Bundle Adjustment we mentioned, VIBA, fine-tunes everything. Part B visualizes the key problem. VIBA solves the rolling shutter effect. You can see how each row of the RGB camera's sensor is exposed at a slightly different time, unlike the SLAM camera, which captures everything at once. This time difference is what VIBA so carefully corrects. And this figure gives us a really stark visualization of the very problem that Visual-Inertial Bundle Adjustment is designed to solve. On the left, those red streaks are what are called reprojection vectors. They show how much each point in the scene appears to move, just within the single moment the camera sensor is active. The graph on the right then plots this movement as a reprojection error. And as you can see, that error can be huge, up to 30 pixels or more. An error of that size is exactly what causes the blur and misalignment that their method so effectively eliminates. Okay, so after seeing how large that error can be, this next table gives us the hard numbers to prove how much their solution helps. And what's cool is that these results are from a completely different device, a MetaQuest 3, showing their method isn't just for specialized hardware. The table compares their full system against versions with key parts removed, using a few standard image quality metrics. For peak signal-to-noise ratio and structural similarity, higher scores are better. For LPIPS, a perceptual loss metric, lower is better. And the results are clear. Removing the Visual-Inertial Bundle Adjustment causes a huge drop in quality across the board. Alright, and this next table expands on that, moving beyond just the final image quality to look at the accuracy of the 3D geometry itself. This data comes from the DTC dataset, which has ground truth 3D models to compare against. So, in addition to peak signal-to-noise ratio, we now have metrics for depth and normal error, where lower is better. The depth error tells us how accurate the distances are in the 3D scene, while the normal error measures if the surfaces are oriented correctly. In their full method, it blows the baseline, splat facto, out of the water, especially on that normal error. This shows the reconstructed scene isn't just pretty, it's also structurally much more accurate. Alright, and building on that idea of accuracy, this next table really shows how their full system performs across a whole range of different real-world scenes. This is the ARIA scene dataset, split into challenging outdoor and indoor environments. They compare their method, our Egocentric GS, against baselines like Splat Facto and 3D GS on Move. And across the board, in every single scene, their method comes out on top. Just look at the bike shop scene, a nearly 3-point jump in PSNR, and importantly, removing any single piece of their system, like the Visual-Inertial Bundle Adjustment, consistently lowers the score, proving every component is pulling its weight. To wrap things up, what this research really shows is the power of tightly integrating motion sensor data, that visual inertial information, directly into the 3D reconstruction pipeline. It's not just about a better algorithm, it's about using all the data available from devices like AR glasses to build incredibly accurate and photoreal digital twins of our world. This work is a huge step forward for creating truly immersive, augmented reality experiences. That's all for this AI Research Roundup. Thanks for tuning in, and I'll see you next time.